Okay, this is going to be a quick review of the parent graphs and their domain and range. Okay, so all of these right here are the parent graphs. So the constant graph, that's when y is equal to any number. So let's call this 3. We could have y is equal, we could name that 3000. It doesn't matter. When y is equal to a number, it's going to be a horizontal line. And notice any x, the domain for that, I shouldn't say x value in this case, that's misleading. The domain for that, if the function is f of x is equal to 3, which is what that line is right there, that's the equation of that line, it doesn't matter what x value we look at, the height's going to be a height of 3. So that means we can put any x value in and we're going to get the height of 3. So the domain values, negative infinity to positive infinity. But notice the range. The range only has one height, and that's the height of the number. So if we said f of x, and let's call that 3000, then the range would be 3000. But the domain would say the same. Okay, the next parent graph, the linear graph, y is equal to x. That's a play off of y equals mx plus b, but the parent graph is this. And notice the arrows keep going in both directions. That means we can put any value in for x. So its domain is negative infinity to positive infinity. And notice in the set notation, it means all the real numbers. And all the real numbers is sometimes shown as, there's kind of a double R. So it looks like it's a blurry R, but that means all real numbers. So some teachers prefer all real numbers. Some teachers prefer negative infinity to positive infinity. All right, absolute value graph. Its lowest point is right there. So if you had a y is equal to the absolute value of x plus 5, well then that graph would be shifted up and would look like this. Now its lowest point. So whatever is that value right here, that is going to be the range. So in this case, in the parent graph, the lowest value is 0, so it's going to go from 0 to positive infinity. But if you notice, we can take the absolute value of any x. So these x's go on infinitely, and these x's go on infinitely. So again, x will be all of the real numbers, or negative infinity to positive infinity. Okay, for the quadratic, kind of is similar to the absolute value in that it will have a minimum or a maxima, minima or maxima. And that point is called the vertex. So the range will be the vertex headed towards positive infinity, or, the range will be negative infinity up to 0. It'll look something like that. And then in set notation, y such that y is greater than or equal to 0, or y such that y is less than or equal to 0. So that's set notation. But notice the domain, negative infinity to positive infinity. So the most important thing to remember, that for all polynomials, so any x to the positive integer, so x to the first, a quadratic, so this is linear, this is quadratic, cubic, etc., the domain always will be negative infinity to positive infinity. So notice for the cubic, for the exponential graph, same thing, because that graph, you can put any value into that exponent. any value of x, and it'll show up on the graph. For a quadratic, the range will be whatever the y value in the minima or maxima will be, and that will be what the range is. For a cubic, much like, oh, I didn't mention the linear graph, much like the linear, see how that arrow is going infinitely up and infinitely down? So it's also all reals, or negative infinity to positive infinity. Same with cubic. And what do they have in common? Any polynomial where it's x to the odd, both domain and range are all the real numbers, or negative infinity to positive infinity. So any x to the odd, so if this were x to the fifth, this would be domain and range. If you had an x to the even, x to the fourth, x to the 100th, it would fit this criteria. The domain would still be negative infinity to positive infinity, but the range would be the vertex, the y value of the vertex point. All right, so this is the parent graph of the exponential. And again, you could always put in the table of values, right? So since the domain can be either, you could put in these x values in the calculator to get your y values. If you needed to graph, here is the parent graph of the square root. That should make sense. The square root of 0 is 0. The square root of 1 is 1. The square root, we come out here a little bit, of 4 is up there at 2. Notice we can't have any negative numbers. You can't take the square root of negative numbers unless you're getting into the imaginary plane, which is what we would not be doing for this. So in this case, notice the domain and the range have a restriction. So for the parent graph, since it starts right here, the square root of 0 is 0. If you did your table of values, if you put in x, you get y as 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4, etc. But notice the domain and range for the parent graph. Now, if this shifts, if inside here we say subtract 3, well, what's the opposite of negative 3? Positive 3. So this whole graph would be moved, and it would start here, and it would look like that. And so the range would then be 3. The domain would be, sorry if I said range. The range would still be 0, but if we said plus 4, so now the graph would be moved up 4, and it would look like this. Well, then 4 to positive infinity would be the range. Okay. Cube root is much like the cubic graph. It's just the inverse. The cubic looks like this. They are inverses of each other. So their domain and range are the same. And remember, that's an x to the odd. It's x to the 1/3. Remember, a cube root is the same as the 1/3 power. So domain and range are both all reals. Here's what the logarithmic parent graph looks like. The domain. That was clearly an error on my part. Oops. I'll have to fix that note sheet. Oh, no, I had it correct. The reason why there is an open parentheses there is there's an asymptote. The log of 0 for any base is undefined. So that means there's an asymptote right there. And an asymptote gets an open parentheses. But notice the range Even though it looks like it's going only sideways, it's slowly, infinitely going up, and it's quickly, infinitely going down. So all reals. And remember, the log and exponents, they're inverses. And look at their, so if I say this is the range, now I'll call this the domain, and this the range. Look at, they're inverses of each other. All right. And then finally, oops, this took too long for a quick graph. This is what, these are both rational graphs, but this is sometimes referred to as the reciprocal graph. And they have limitations because both the x-axis and the y-axis for the parent graph are asymptotes. So you're going to have a graph, a domain and range, that is a union set. For the domain, it's the x's less than 0 and the x's greater than 0. For the range, it's the y's greater than 0 and the y's less than 0. And for this rational graph, when you've got a squared in the denominator, the graph looks like this. If there would have been a negative sign, then the graph would look like this. So, but notice they're still asymptotes, so the domain is still going to be a union, but now the range is only going in one direction. It's either infinitely going up, or it would be negative infinity up to 0 for this case. And then this is what the greatest integer function looks like. The domain can be any number, but the answer, remember, for the greatest integer function will be integers only. It'll be all the integers, but integers only. All right, that is it for domain and range and parent graphs.